Well, hello again, sports fans. Welcome to another exciting edition of Physics 12. This is lesson 3.5, and we're going to start to look at one-dimensional momentum and impulse. And most of us have an idea as to what we sort of mean by momentum, but you might not understand the real technical part of it. You know, what do we really mean in physics when we talk about momentum? So most of us, when we think of momentum, we think of, you know, fairly large objects like a railway train. Trains have momentum. They take a long time to stop, you know, so there's a lot of mass moving down the tracks. And you might think of like an ocean liner, some kind of a tanker, also has momentum. You know, it's got a lot of mass, and it takes a long time for a tanker ship to stop. So we think of those things as being having to do with momentum, or in sports, like for example, a linebacker in a football game. These guys have momentum. I mean, they're big and they're fast. And we're talking lots of momentum there with for these particular athletes. But let's be a little bit more precise about our definition of momentum and what we actually mean by that. And let's first look at its relation to force. And so this is just a diagram of the cue ball on a pool table that's hitting another ball. And there's a collision, and there's an exchange of momentum there. And we'll look at collisions a little bit more closely over the next couple of lessons. But this is the sort of thing that we're talking about with momentum. So the cue ball, as it's struck with the pool cue, it's got a certain amount of momentum, and it may or may not hit another ball. I know sometimes we don't actually make contact with the ball that we're aiming for on the pool table. So there may or may not be a collision here. So momentum is a vector, and it's symbolized by the symbol a lowercase p. So a lowercase p, and is defined as it's the mass of an object times its velocity. So that's just simply what momentum is. So it's got to be a vector because velocity is a vector times this scalar, which is the mass of the object. So the momentum of an object, it is a vector, and it's just simply the mass times its velocity. So if you had that thought of a railway train having a lot of momentum, well, you know, that's probably a good idea that it does have a lot of momentum because it has a huge amount of mass. But you can think of something fairly small. If it has a large velocity, it would also have a large momentum as well. For example, the bullet coming out of the end of a rifle. You know, you're talking a lot of momentum there as well. It just happens to be a smaller mass. So the rate of change of momentum now is equal to the net force on the object. So in order to have a change of momentum, there has to be a force applied to the object in order to get that change in momentum. And so the sum of all the forces acting on an object will equal the change in momentum over the certain amount of time that the force is acting on that particular object. And so we generally talk about the change in momentum with respect to the amount of time that the force is being applied to the object for. So this can be shown using Newton's second law. And this is the form that normally we look at. So the change of momentum equals the net force on an object times the amount of time that the force is being applied for. All right, so now that we've got a little bit more clearly defined, let's look at some examples of this. So here's a tennis ball that's being struck by a racket. And so obviously the tennis ball is going to have a change in momentum due to being struck by that tennis racket. So during a collision such as this, then the objects are deformed due to the large forces involved. And so if you can capture these images here, like the tennis ball here being struck by the racket, and so you get some deformity of the tennis ball itself, as well as the strings in the racket. Some other examples of this, if you've watched slow motion video of a golf ball being struck by a golf club, again you get some deformity of both the golf ball and the club. Another example of this could be a baseball being struck by a bat. You probably don't see as much deformity there because the bat and the ball are fairly hard objects, so you don't see quite as much deformity. However, this is a nice example of it right here. So since the force that's being applied to the object, in this case the tennis ball, will equal its change in momentum divided by the amount of time that the force is being applied to that object, in this case the tennis ball. And that, of course, we can rewrite this way. So force times the amount of time that the force is being applied for, that will equal the change in momentum of the object. And it just so happens that the definition of impulse happens to be the change in momentum. So as you can see, these are the same thing. The change in momentum is the same as impulse. So when you hear the term impulse, then you know that we're talking about the change in momentum. And that is equal to the force that's being applied to the object times the amount of time that the force is being applied to that object. And in this case, it will be quite a small amount of time, actually. So collisions and impulse then. So since the time of the collision is very short, then we don't need to worry about the exact time dependence of the force. And we can use the average force instead. So that makes it a whole lot easier, actually, because the force that's actually applied to this object is quite complex. And so if you were to actually graph the force versus time of a collision like this, you would get a fairly complex kind of a graph. So it's a whole lot easier just to go with average force, which is what we usually do. Here's an example of that, and this is how the force actually might look, something like this. And the amount of time that the force is being applied for is often quite small in these kinds of collisions. And so what we do then is we would just use the average force times the amount of time that it's applied for. So again, we're sort of going with area here. So we sort of approximate the area under this graph here, and that would be the average force times the time that it's being applied for. All right. So impulse then, impulse tells us, again, impulse is the change in momentum. So it tells us we can get the same change in momentum either using a very large force over a small amount of time, or a small force over a large amount of time. And this is exactly the reasoning behind minimizing injury in motor vehicle accidents, etc., with respect to the use of airbags and anything else to create a soft landing. So anytime that you want to absorb an impulse or bring something to a stop, you want to do that over the longest period of time that you can. Because if you increase the amount of time, you decrease the amount of force. So small amount of time, large force. And it makes sense. So when you think about it, something stopping in a very short amount of time creates a lot of trauma. So like, for example, in motor vehicle accidents, when something runs into a very solid object, the change in momentum is very, very sudden, very abrupt, very short amount of time, so huge forces involved on the person or the people inside the vehicle. So if you can absorb some of that over a longer period of time, so then you'll need a smaller force to, or a smaller force will be endured by the people inside of a vehicle. So that's the whole basis behind it, actually. So again, also if you're jumping down from something and you're landing, by bending your knees, what you're actually doing is you're doing the same sort of thing. You're taking that force and applying it over a longer period of time. So you need a smaller force. You can imagine if you jump off something and you land with straight legs, that's going to create a whole bunch more force through your body because you're stopping in a much smaller amount of time. But by bending your knees, you're taking that impulse, that change in momentum over a longer period of time, and so the force and hence the trauma experienced by the body is much less. So this is why you should bend your knees when you land, or why airbags work, and why landing on a pillow hurts less than landing on concrete. So all you're doing is you're taking that impulse and you're spreading it over a larger amount of time. Okay, so that's the basis of momentum. And so momentum is defined as just simply the amount of mass of an object times its velocity. And impulse, as we said, is the change in velocity. And it's measured by the force times the amount of time that the force is being applied to the object.